break because there were so many questions. Okay, so this is, you have my admiration. So I hope this was worth coming back from a short tea break for. So this morning, Rana and I together are going to be talking about vibration isolation, and we've divided it up more or less along passive techniques, which I'm going to cover, and then active and other clever, deep, advanced things that Rana is going to talk about in the second hour of this session. And oh, right, of course. So here's my orientation schedule slide, but I need to warn you that Ron and I are going to make some adjustments this afternoon. And instead of my talking about thermal noise when we come back from lunch, I'm going to give a short lecture on optics of Fabry-Perot cavities before Rana goes into some more optics topics. And that makes sense for several reasons, not least of which is Rana is down for 2 one-hour talks after mine. This will make a nice workout and working out of the schedule. And then tomorrow morning I'll come back with my thermal noise talk, and Rana, you have one on that topic as well, right? Okay. So now here's the outline for what I'll do in this hour. I want to use this topic in part as well, I will use it, or it naturally will use itself, to illustrate some of the ideas that I spoke about yesterday afternoon in the talk called Theory of Linear Systems. So you'll see that both at the beginning when I talk about interpreting power spectra for purposes of setting performance goals, but also throughout the description of seismic isolators. You will have to be always talking about power spectra, frequency responses. All those tools will come in here. So I think it's a nice topic to have followed what I spoke about yesterday. And that's so nice that it makes up for something that I, as a sometime physics snob, have to fight against. When you consider shot noise, wow, fundamental physics that gets you towards the frontiers of quantum mechanics. Isn't that amazing? Tomorrow morning when we talk about thermal noise, it's really, really deep stuff about the nature of dissipation and what's the relationship between the macroscopic and microscopic. Or another way of saying the elevator snobbery that I have, H bar is all over a description of shot noise. K. Boltzmann is all over a description of thermal noise. Seismic noise has nothing to do with physics whatsoever. It is just some dirt that the Earth throws at our experiment that we have to take seriously because it's such a big noise. Okay? So at that level, I feel sort of soiled to have to work on this. On the other hand, it's really important, and the tools used to save us from it are great. Okay, so we work with what God gives us, and seismic noise is one of those things. So I'll talk a bit about how strong seismic noise is, how much we need to attenuate it to do our measurement, how passive isolators work, and then I'll transition into some things that will warm you up for Rana's talk. Okay, so I was just making a distinction between seismic noise and thermal noise, one being fundamental, namely thermal noise, and seismic noise being merely ubiquitous. But on the other hand, they live together in the category of noise effects that move mirrors, displacement noises, unlike shot noise, which is a readout noise. So depending on what you care about, the categories move around. Okay. Now here's a slide I showed when I was trying to scare everyone. This is one of the noise sources that's that's big, really big. Seismic noise has an RMS displacement for, if you care about things that happen around 1 hertz, of a micrometer. A wavelength of light. I mean, that's tremendously large. So clearly we have to do something about it. Now, I want to pause for a moment, and I hope this isn't belaboring a point, but it might be helpful to a few people to be very explicit about 2 different ways we quote a sensitivity goal, or an amount of noise that we can tolerate. Rana and I think I can accuse Ali of this as well, have kind of switched back and forth sometimes between talking about noise levels in spectral language, in the language of something per root hertz. And I know I at least have often wanted to also talk about just sort of an overall RMS, or a mean squared noise level. And unless one's fluent about going back and forth between those 2, it's easy to get confused because the numbers are close but not that close. So I want to take this opportunity to do just a pedagogical example which may reinforce what I was saying yesterday about interpreting a power spectrum. So let's say, because I'm stuck in the 20th century, I remember when I always said that the LIGO target is HRMS of 10 to the minus 21. And it doesn't matter which number I pick, but that's the one that's stuck in my head. Now, from the first moment, Rana especially, but all of us, have been showing us graphs of the amplitude spectral density of a noise in the units, not dimensionless units, but the units appropriate to an amplitude spectral density of an inherently dimensionless quantity, namely per root hertz. So if I was going to read off something here on this scale, and what needs to be the number here on this scale so that I'm talking about a measurement that can be sensitive to something whose RMS size is 10 to the minus 21. That's the exercise I want to walk us through, just to make sure that we're all on the same page. So the translation is not unique. The translation has to do with what kind of measurement you are going to do in the presence of this noise. This noise spectrum is this noise spectrum, but every measurement that you do in the presence of this noise has the possibility of yielding a different size signal that you might see in the presence of this noise. So let me illustrate that. I maybe said that in a confusing way. What if I think I've got a gravity wave signal, h of t, whose characteristic duration is, I'll pick 10 milliseconds, and it's only got of order a cycle, or maybe half a cycle, something like that. So that's also got a characteristic frequency, the way I've driven it, of about 1 over this, or of order 100 hertz. So I want to know about the characteristic frequency of the signal that I'm looking for. But I also, before I'm going to make my translation from a spectrum of noise to an RMS, I need to know what is the bandwidth of the signal that I'm looking for. And if I've got something as short in duration as 1 cycle, the bandwidth is of order the frequency. And therefore, in this case, it's of order 100 hertz. So if I make a well-constructed search for this kind of signal, such as the kind of matched template search I described yesterday, doing the cross-correlation between a template and the noisy time series, in spectral language, I'm going to be admitting about 100 hertz's worth of noise, centered more or less around 100 hertz. And it's that noise that's going to contribute to the RMS of the result of the output of my cross-correlation search. So remember that slide I showed yesterday with input noise, then the template that gets slid along, and then how much quieter the output time series is. What I'm about to do is calculate what is the RMS of this output of a matched filter search for this kind of signal. Okay? So what I need to do is find how much noise comes from this part of my spectrum. So I'm inviting myself to do an integral over this part of the spectrum, but somebody shout out what I'd better not do. Can I just integrate up this h of f between 100 hertz? Stop me before I make a mistake. Square it first. Okay. So, all right. So I need my h squared of f in units of per hertz. Now integrate over 100 hertz, centered on 100 hertz. And if my target for that answer is 10 to the minus 21 as a root mean squared, then, okay, we've been looking at the answer up here. That says that I actually need a spectral density here, an amplitude spectral density of 10 to the minus 22 per root hertz. Okay? So whenever you think you're about to be confused, know that the noise spectrum doesn't depend on the kind of signal search you're about to do, but the RMS that you would want to quote always does. And you'd better make the translation by this kind of, not too painful, but a set of steps that you need to do. Okay. I hope that wasn't belaboring the obvious. I hope it was helpful at least to some of you all. Okay. Now, seismic noise, our search is naturally searching for something where the natural way of characterizing its strength is the strain amplitude h. Seismic noise comes into our instrument as a displacement that can in principle move the mirrors, and that will move the mirrors even though we're going to filter it. And we need the translation between a displacement noise and the strain noise that it looks like in our output. And with arms, each of which have a test mass at each end, there are 4 different prime places for seismic noise to come in. They are almost entirely uncorrelated, those 4 places. So we've got 4 noise terms that add in quadrature, and as a result, the translation is x over L, but square root of 4 contributions, or 2x over L, is the translation between a target noise in strain and a target noise in displacement. Okay, I'll do that if that's more dignified. Thank you. And so the result of all of this is that we need, for a 4-kilometer system, a displacement noise in the vicinity of 100 hertz, if that's where we're looking for signals, of 2 times 10 to the minus 19 meters per root hertz. Okay? So that's my displacement goal that I would say my seismic isolation is a success. At least it's a success for a search near 100 hertz. And the statement of whether I have a good seismic isolation system or a bad seismic isolation system depends entirely on where I want to look for signals. And it's worse than that. It is guaranteed that there will be some frequency ranges for which any seismic isolation system is a failure. They work well at high frequencies. They don't work very well at low frequencies. We struggle to do better at low frequencies, but they always fail in the limit of low frequencies. So, very good. That's the right optimistic answer. That's the young leader telling us. Okay, but so this is one of several aspects of our discipline that is tragic. It is guaranteed to be a partial failure. But there's also been some amazing successes too, and I'll trumpet the successes mostly from now on. No, you're going to talk about the bright shining future that's even better. Okay. You always get to talk about the bright shining future that's better. All right. Now, I'm going to start by showing a graph and then flip back to that slide with the numbers. I have to just assert what the seismic noise spectrum is that is my input. And not only is this something that a physicist can't derive from any kind of first principles, but it's in fact pretty darn variable. Different sites on the Earth, some are really terrible, some are only somewhat terrible. It's also a time varying thing. There's frequency bands that depend strongly on the weather, either the weather right nearby or the weather at the nearest part of the ocean. So this is as unfundamental as it gets. But for purposes of getting through a talk at a school, I'm going to say this graph represents more or less what the seismic noise input might be at a typical place. And let me walk you through this graph because from the back I'm sure you can't see the scales. So this is a logarithmic scale of frequency, logarithmic scale of displacement noise in meters per root hertz, from 10 hertz over here to 10 kilohertz. And up at the top here is 10 to the minus 8 meters per root hertz, and this is 10 to the minus 10, 10 to the minus 12, 10 to the minus 14. So here is a rough approximation to the seismic noise power spectrum. And note that over this entire range, the noise is much higher than our target, which was 2 times 10 to the minus 19. So our target's down here. Each of these tick marks is 2 orders of magnitude. So we start out with a huge challenge. We need isolation 3, 4, 5, 7, 8 orders of magnitude. And if we want to see this in numbers, what I drew was a power loss above 10 hertz that had a 1 over frequency squared characteristic and this coefficient. So if I want to stick for illustrative purposes with a target frequency of 100 hertz, I can read off of that graph that my input noise at that frequency has an amplitude spectral density of 10 to the minus 11 meters per root hertz. So I'm about 7 orders of magnitude away from success when I start. Okay? Or 8. I'm sorry, I'm 8. About 8 orders of magnitude away. So there's the graph. And now, remember that here we are in the dirty real world. When I was pretending to talk as a relativist, I was talking about free masses. And then Ramanna said, you better explain to people what you mean by free, because they're not really being dropped. They're not really free. They need to be free to move in response to gravitational disturbances, and we invented the pendulum suspension as a good way to approximate freedom. And they also need to be free from large disturbances in the environment. Otherwise, the signal is swamped. And maybe, if we're lucky, hint, hint, the solution to one is related to the solution to the other. It is. Okay. Now, let me talk a little bit more in strategic terms before talking about actual kinds of solutions. So this first point that I wrote on this view graph is a restatement of my claim that we'll never have enough seismic isolation. We can solve it, as I'll convince you, it's already been solved very well at high frequencies. There will always be a low frequency band at which we fail. We could always want more to extend our sensitive frequency range down to lower frequencies, to the left on all these graphs. Okay, so we always want to build as much seismic isolation as we can. Secondly, knowing that we're going to fail at low frequencies reminds us that we've got a measurement problem that may seem really, it may seem impossible from a different point of view. What it means is that my mirrors are going to be moving by numbers like a micron in spite of what I'm doing, no matter how much seismic isolation I put in. And so I have to figure out a way to make this interferometer with free masses fulfill the fundamental requirement of an interferometer, namely that the mirrors be near some operating point where our cavities are in resonance, that they're aimed in the right place, and precisely where the motions are biggest, my isolation system is the biggest failure. Which means I have a problem which you would think seismic isolation would solve, but it doesn't. I need a different kind of solution entirely, and that solution is to make use of feedback control and other kinds of control systems to supplement the seismic isolation that's always going to have failed at low frequencies and perform the function of holding all the mirrors at the right operating points in spite of the fact that they would otherwise be moving by these large amounts. And I need to do it in such a way that A, they stay at the operating point, and B, that can be seen to allow us to treat the instrument as linear in spite of the fact that the input should move it through the huge nonlinearity of our optics. Let me start that sentence over. If I had mirrors moving by this much, we would hop out of resonance of cavities, or even if I were using a Michelson, we would go from one fringe to another. The thing just wouldn't work. There would be no way of reading off an output and getting any kind of interpretation out of it. If, on the other hand, I use feedback control to lock my mirrors at good operating points with respect to each other at low frequencies, then I've both solved, I have made a situation where then small motions at high frequencies are exploring a linear characteristic and allowing me to have something interpretable, even though at low frequencies there's a huge motion. Okay, I will try to make that clear as we go along, either today or when I talk about servos tomorrow afternoon. Okay, so now let's finally move on to how we solve the problem. Here's a reminder of the payoff of yesterday's linear systems lecture. This is the frequency response of a simple harmonic oscillator. There's a resonance frequency. That's the most distinctive thing when you first think about a mass on a spring or a mass hung from a wire. But for our point of view as thinking about seismic noise and seismic isolation, the most interesting thing is that the frequency response falls like 1 over f squared to at all frequencies above the resonance, or all in quotes. I'll qualify that in a moment. But the ideal mass on a spring does have just this 1 over f squared transmission above the resonance. And we inserted the pendulum suspension, at least initially, conceptually, to make our masses be free enough, approximately free enough, so that we were doing a general relativity experiment, looking for gravitational waves. But for free comes along the fact that that's a seismic stage of seismic isolation as well. So we get this factor of 1 over f squared isolation in the motion of the mirror compared with the input motion we already have that built into our plans. And here are some old pictures, some 20th century pictures, well, no, early 21st century pictures maybe, of a pendulum suspension. These are, well, this is a recycling mirror, right? And this looks like an actual test mass going in. As you can see, the 10 kilogram scale initial LIGO mirrors, and what's hard to see in pictures like this is the steel wire that wrapped around the bottom of that mirror and is held in a clamp up around there. Pardon? Yes, everything looks small. And so 20th century too. Yes. All right, and here's a slide I actually stole from a talk that Ramanna gave at Syracuse some years ago. Hope you recognize your lines. Yeah, okay. So here's some more close-up views of a test mass. This part of the picture I especially like. This is a close-up view of the side of a test mass where you can actually pick out the wire that is in contact with the cylindrical surface, the barrel surface of the test mass until about here, and then it goes over a little cylindrical rod of glass with a little groove in it, and then goes on up to the clamp up at the top. What you see here, the stuff that's the most visible, are all the local sensors and controllers. Here is a magnet that's part of the coil magnet controller system called OSIMs. Here you can see the coil forms and the coils better. So the initial LIGO test mass control system had 4 sensor pushers on the back and 1 on the side. Here's some, you can see the clamping mechanism to hold things in place when they need to be held in place. Okay. Now, let's ask the question. We have a vibration isolator already built into our plans. Does it solve our need for vibration isolation? Here's our input spectrum. Here, this input spectrum is multiplied by 1 over f squared. And I artfully cut the graph off at 10 hertz so I don't have to draw the resonance peak or anything else that's going on. And I've multiplied this by the 1 over f squared factor, where I put the resonance down at 1 hertz. And I can just do this with a ruler. Okay? Before I had MATLAB, I would do this on a ruler with graph paper. It's that simple. So the question is, do we get to 2 times 10 to the minus 19 meters per root hertz with this isolation system? Well, maybe around 1 kilohertz. So if our target was kilohertz signals, we could declare success. And we know of some kilohertz signals that we're looking for, so in that sense it's already good. But we know of a lot of signals where most of the action is down around 100 hertz or down around 50 or 40. And so from that point of view, it's a miserable failure. We're still 1, 2, 3, 4 orders of magnitude away from success at 100 hertz. So okay, but not there by a long shot yet. All right. Now, we can use the same trick again. There's nothing that says we're required to hang the top of our pendulum wires from something that's rigidly connected to the ground. We can hang them from something that is itself suspended, from a mass that is itself suspended by a spring from the outside world. Or we can attach several such stages in series. So wires can go to a mass, which is connected by a spring, to another mass, connected by a spring to another mass. And you can build these so-called isolation stacks of several stages. And when you do, here's another thing that is especially easy in the frequency domain, since I'm extolling the power of the frequency domain. And that is, when you have a cascade of vibration isolation systems, the high frequency limit of the frequency response of that set of cascaded things is in fact just the frequency response of one stage, resonant frequency over f squared, raised to the power of the number of stages that you cascade. So if I have 3 stages, we get f naught over f to the 6. And so in principle, if we're interested, if we know we're going to fail and we just have a target of above some frequency, we need to be below a target. This is a prescription for telling us, okay, just build 3 stages or 4, start exploring it, and you will get to good enough performance. So here is, again, our input amplitude spectral density of noise. And now I've multiplied this by the frequency response of the pendulum at 1 hertz and 3 additional stages of mass spring isolation where the resonant frequencies of those 3 stages were at 3 hertz. And now, look what I've got. Something that's really steep and hits our target around 30 or 40 hertz. So if we're willing to declare success by reaching our target from 30 hertz onward, this is a success. And it was declared to be a success for initial LIGO. Would not come close to meeting our goals for advanced LIGO. So after I sit down and Ramanna stands up to speak to you all, you'll see the rather different technology that's being used in advanced LIGO. But it's pretty cool that as dramatic a problem as needing 8 orders of magnitude of isolation can be achieved by such conceptually simple means that were only somewhat hard to engineer, and not even really terribly hard. Yes, Tarun.
Ensure that the resonant frequency of each stage is the same?
No, you can in principle make them various frequencies, and I've already done that in the sense of saying we had a 1 hertz pendulum and then those other stages were at 3 hertz. There's no particular reason they have to match. It's kind of okay. Now, one thing that I was sort of artfully vague about when I displayed this statement is true for frequencies that are large compared to all of the resonant frequencies in the system. However, if I wanted to make a statement about what's the frequency response in the frequency range where there are resonances, I don't get just a simple multiplication of the frequency response of each stage in this case, because I'm not really cascading things the way you'll see me do when I'm talking about all the electronics that goes in a servo loop. There's real back reaction of the dynamics of one of these masses on another, unless you go to a limit that we couldn't afford to do of having each stage higher up be a lot more massive than the things underneath. So it's actually a non-trivial dynamics problem to figure out exactly what the modes, the coupled modes are down in the mode frequency region. But in spite of the fact that that thing is complicated, this is simple. Now, as I wrote it, yeah, I wrote it as if they all had the same f naught, but I could have written, f naught over f squared times f1 over f squared times f2. That's a slightly cleaner way of writing it.
What limits f naught from choosing of f naught much smaller? Is just the size of the thing?
It is the size of it. If you make springs in a dumb way, that is the way I kept inventing them over and over, there's an interesting theorem that tells you a limit on simple-minded ways of doing this. For any kind of spring that supports weight, okay, and stretches, like the coil springs I will show you that implement this, or any other elastic thing that deforms downward under the load, the stretch of the spring when you load it is equal to the length of an equivalent pendulum that has the same resonant frequency. So a 1 hertz pendulum is the better part of a meter. If I want to make an ordinary kind of passive isolation thing, it deforms by a meter, close to a meter, when I load it. Now, there's clever things you can do. There's sort of pre-stressing things, and some of those tricks are used in advanced LIGO, and we stole some of them from advanced Virgo, well, from initial Virgo, in fact. So there's some ways around it, but that's one indication that it's a tremendous engineering challenge to make really soft passive isolation. You have to be very clever. There's another, probably more fundamental limit even than that, and that is, I will illustrate this in a little bit, but it's appropriate to your question right now. I keep writing this 1 over f squared per stage characteristic, and that is more or less true, but it's not true to arbitrarily high frequencies, because any physical spring, be it a coil spring, a cantilever that bends, a pendulum, not only is a spring, but it has some mass, which means it has some internal modes of vibration. And once you include the physics of those internal modes, you find something that's kind of distressing. Here's my 1 over frequency squared characteristic until I encounter my first normal mode. And then I'll see a bump. And then, oh, maybe it was going to recover. Ah, but you know what? There's another one. And they're crowded. And as a result, this 1 over frequency squared characteristic basically takes me from no isolation to a situation where I've got a fair amount, and then it more or less levels off. And for any particular kind of design of spring, I make this softer to move this to the left. These almost always move to the left more. Okay, so it is physics. It's not just engineering. I mean, there's real laws of nature that come into this. But the engineering results, since we don't love seismic isolators themselves, we want to hunt for gravity waves, for us it's an engineering problem of the first order that it's hard to make ultra-soft passive isolation. Now, having said that, I should maybe steal a tiny bit of Rana's thunder. I'm using this to make you say, okay, you just can't do it. You've got to go to active systems. And that is the design choice that LIGO made, as Rana will describe. However, Virgo has, by exquisitely aggressive engineering, managed to, from the initial Virgo era onward, have really great seismic isolation with soft, mostly, it's mainly a passive isolation. Sometimes we get in theological disputes, oh, it's so tippy, it has to be damped and controlled, so it's really active too. But the isolation mainly comes from the softness of 7 stages of isolation. So you can push farther than LIGO did in the passive direction. And I'll show a diagram or two. Are there any diagrams in your talk of what Virgo does? Okay, so we'll let Rana explain it in detail how well they did succeed. They were fighting the same physics, but they did a better job. Okay, and but I don't think there'll be another generation of better passive isolation beyond what they did. That was heroic. Okay, so that's gonna 3 stages of 3 hertz added to the 1 hertz pendulum met the initial LIGO target. Now, both we and Virgo confronted the fact that I'm describing on this slide, namely that even though we're making a measurement that involves mainly 1 horizontal degree of freedom of each mass, that's really what it should do, we need to engineer into our isolation system a fair amount, almost as much vertical isolation as horizontal isolation. And there's a couple of reasons for this. One is it's really hard to make things like this that would have a huge amount of vertical motion and not have any cross-coupling into horizontal motion by slight imbalances or whatever. But even if we could ultra exquisitely align our mechanics, our measurement isn't precisely in a horizontal plane. Already at a 4-kilometer baseline, there's a non-negligible angle between the vertical at one end and the line that that connects, that takes the laser to the other mirror. So vertical motions locally, in fact, couple into the optical path. And as a result, we made sure that, especially because our pendulum suspension right there at the test mass is so much stiffer in the vertical than horizontal, it gives very, very little isolation in the vertical. We made sure that we had more or less quasi-isotropic isolation for the rest. Those 3 hertz things were designed to be close to as good in the vertical direction as the horizontal direction. And this reminds me to give due credit once again to Joe Weber, the inventor of the first gravity wave detector, who confronted the vibration isolation challenge. He could succeed if he succeeded at around 1 kilohertz. He invented precisely this solution of mass spring, mass spring, mass spring, in his case with blocks of lead separated by blocks of rubber. But in a way, as in many things, we're sort of following in his footsteps. So here's a photograph. I'm going to show you a few things about the initial LIGO isolation system before I show you some cleverer ones. Here are some pretty well engineered springs. These are copper tubes filled with a highly lossy elastomer to try to make sure that these peaks were as low as possible, and to make sure that the low frequency peaks also weren't too big. And here you can see those springs in place in a spring, mass, spring, mass, spring, mass stack. There's one, here's another, there's a third, and there were 4 of these around.
The last spring is hiding on top.
Oh, okay, I can't quite see it, but I believe you. Okay. Oh, pardon?
Yeah.
Right, oh, right there. Yeah. Okay. And then this is a kind of goony looking quasi-rigid structure that passed through a hole in this plate and held an optical table to the underside of which the pendulum suspension was bolted. So here's a space that's more or less rigidly connected to the outside world, and 1 stage, 2, 3, 4. Is that really a spring? Okay. So it's actually 4. On, then down to the pendulum. And here's another view in an engineering drawing of where it was installed in a so-called BSC chamber. You can't see from this view the optical table just hidden underneath there where the test masses were bolted up, but you can see the stacks. And a similar technology was used for other vacuum chambers, the ones we call hams, that had components that required less vibration isolation, supported a table to which things were mounted on the top. And when I said, oh, that looks like a recycling mirror, it lived on a table like this. So here's sort of the overall scale, and I stand about this tall there, to give you an overall scale. Here's another view now, an actual photograph of isolators installed in a ham chamber before the optics were built up on them. And here is the frequency response as measured in air for this isolation system. And you see 3 resonances for spring mass, spring mass, spring mass. And then you see isolation falling pretty steeply, as you'd expect. And then you see all this junk, which we're pretty sure was not a failure of the frequency response of the system. It wasn't that effect, but this was acoustic short-circuiting of the measurement. It was the driver making so much noise that it directly shook the most isolated part, rather than sending a mechanical vibration through the metal parts. Here is a measurement of the frequency response of the isolation stack that I was showing you before, the one that goes in the more critical systems. Here is 1, 2, 3, 4 peaks, a really steep frequency response, and then no proof that we had anything more than the internal resonance effect. But we've got a number of orders of magnitude before it levels off. So this is a really successful isolation system. This is giving us good isolation by around 30 hertz. Okay. So we had 6 orders of magnitude by that measurement in the LIGO stack. And that's enough to have hit our target. Now, let me show you this extremely well-engineered isolation system developed by Virgo. Here's the test mass way down here. Here's another block that they call the marionetta to do control, which is in turn suspended as a pendulum stage from this object, suspended as a pendulum from this object, from this one, from this one, from this one, and from up here. And this whole tower is an inverted pendulum of a very low frequency that gives some isolation as well. Now, what's truly impressive to me about this isolation system is that even though it's built around pendulums, you may have heard me say a few minutes ago that the problem with pendulums is they tend to be really stiff in the vertical direction if you rely just on the compliance of the wires. These things are not simple mass blocks, but they are things that were engineered to have springs about as soft in the vertical direction as the resonant frequencies associated with these pendulums. And as a result, the isolation was close enough to isotropic that you could ignore the vertical noise problem and say, okay, if I know my transfer function, my frequency response for horizontal input to horizontal output, I'm really estimating my performance. And here is an amplitude spectral density of input noise at the Virgo site, and that input noise multiplied by the measured frequency response of this isolation system. And you can see that it achieves really exquisite performance starting around 3 hertz. So that's as good as we would need for an advanced era search. So Virgo doesn't need to put in a whole new isolation system for advanced Virgo, even though LIGO is putting in something brand new and from scratch. Here is a picture of an isolation system designed for and installed in GEO 600. It is going up from the bottom, test mass suspended as a pendulum from an intermediate mass, which is in turn suspended from a structure that has some ability to move horizontally, but also has cantilever springs for vertical isolation, which is in turn suspended from more cantilever springs. And these cantilever springs are highly engineered things of really wonderful alloys and solve to a great degree the vertical noise problem as well. And this heritage of doing better than I said you would do naturally with a pendulum by building in vertical compliance. And a lot of other details of this geopendulum was the heritage that led to the advanced LIGO test mass suspension. And if you see test mass, penultimate mass, structure that is a pendulum but also has vertical compliance, suspended from another structure that is a pendulum but also vertical compliance, suspended from cantilever springs, you see the heritage of those ideas in to applying a fair degree of passive isolation even in the advanced LIGO system. And over here is a graph that shows the frequency response of from the top of this structure on down to the test mass. Okay, 4 resonances and then a very steep fall off. This is part of the vibration isolation story of advanced LIGO, supplemented by the part that Ron is going to tell us in a few minutes. But only part. Here's an engineering drawing of that structure installed underneath this thing that's so complicated that only Rana can walk you through it. I'm not going to try. Pardon? Okay. Now, let me talk about something that is perhaps, oh, yes.
Mirror and another thing above it. They were identical. Yeah.
So this thing
There's a
above
case of- yeah.
is part of, well, it plays 2 roles. It's the first of several additional isolation stages, so it's another pendulum. But it also plays the role of the place closest to the test mass where we think it's safe to put magnetic pushers. So this plays something of the role of the marionetta in the Virgo suspension design, of a place to do your last good steering and controlling.
Steering is done through that. Yeah.
Yes, there's force applied to the ultimate test mass from the reaction mass here, but only longitudinally and only with electrostatic actuators, which have which are there to help make this be the quietest pushing, but they also have a very limited dynamic range. They're very twitchy, very nonlinear. So we need pretty close to the test mass to have the more robust magnetic controllers there. Now, almost certainly the ultimate low frequency limit is a kind of short circuit around vibration isolation system that I've been talking about through the field directly. So I've been talking about a model, which is a pretty darn good model, that the way earth shaking gets to mirror shaking is by the elastic connection between the surface of the earth and the test mass. But it's also the case that if I have, as I do, a disturbance field of the environment around the test mass, it is as if there's all sorts of mass moving around in the vicinity of the test mass. So the fact that the surface of the earth has a fair amount of vertical seismic noise that displaces air and puts a little bit of extra mass over on this side of the test mass, or a little deficiency of mass if the earth goes down on this side of the test mass, causes a time-varying Newtonian gravitational force in the horizontal direction on test masses. Now, you might think it's a small effect, but we're looking for small effects. And so if you put the numbers in, you find with not too many pages of calculation that the coupling between typical vibration field around a test mass and the motion of the test mass is equivalent to a single stage of mass on a spring, with this resonant frequency. Basically, root g rho, where rho is the density of the Earth's material. Now, this is a very low frequency, 10 to the minus 4 hertz, but it's only 1 power of 1 over f squared. And if you start to make the numbers, given how strong seismic noise is at low frequencies, and say, okay, I've got one stage of isolation starting at 10 to the minus 4 hertz, how do I do? You find that by about 3 hertz, you've gone from being below our target sensitivity to above. So, and this is not something that any sort of vibration isolator of the kind that I've been describing has anything to do with. It's a gravitational short circuit around the mechanical parts. So at this point, I throw out my hands and despair. I have some colleagues who don't despair about this, who say, well, we could always place an array of seismometers around and measure the displacement field and calculate the gravitational force. And it may be true. So I don't want to be the mean guy who's going to ruin our Christmas day and say there's nothing you can do about it. But it becomes all of a sudden really hard, a major project, and not, we don't really know for sure how well these models can work. All of which is to say, it's hard enough to make isolation good at low frequencies. There's this extra challenge of Newtonian gravitational noise. At some point, you just want to say, build the darn thing in space. Okay, if you really want to go to low frequencies, just get off to Earth. And this is the key, one of the key motivations for gravity wave detectors in space. Get away from the seismic noise. It also gets away from the thermal noise, from the suspension that you need to hold it up against gravity. There's a few other reasons, but the vibration isolation is as good a one as any. So I'll have something more to say about this on Friday. Let me stop here and hand it over to Ramanna.